The project Interdisciplinary Collaborative Learning and Teaching for Resilient Wood Resources and Innovation in a Digital World is co-funded by the Erasmus Plus program of the European Union. The project is co-funded under the strategic partnership of Erasmus Plus with the duration of 36 months. We say that with Wood Plus, objectives are targeted, opportunities are taken, and make a difference under the Erasmus Plus umbrella. Activities are conducted by a consortium of 4 partners: Mendel University in Brno, Czech Republic, acting as a coordinator, University of Natural Resources and Life Science, Vienna, Austria, University of Hamburg, Germany, University of Ljubljana, Slovenia, and an associated partner, InnovaWood from Belgium. Wood Plus objectives are to support the additional inspiration of the new generation of researchers, to raise the awareness of a wide range of material application, to redesign the learning environment with innovative online modules, to individualize and internationalize the learning pathways. Wood Plus aims to strengthen collaboration in the field of wood science and technology, with particular focus on less used wood species, to achieve brain circulation for students and researchers through strengthened language competencies, to contribute to future-oriented curricula with a broader focus on tree species diversity, to develop green sector skills by promoting industrial exploitation of less used wood species for high value chain utilization by focusing on innovative material developments. Wood Plus also aims to stimulate and support students and researchers' creativity by fostering education diversity networks, to take advantage of diverse educational and research backgrounds, to foster digital competencies by pushing distant learning and innovative learning methods. Wood Plus activities include intellectual outputs such as webinars, ebook, virtual laboratory, experimental design and data analysis, multi-prior events such as conference, and learning, teaching and training activities such as summer schools, workshops, and long-term teaching assignments.
But let's talk what is NDT, what is non-destructive technique. Sorry. It is a kind of evaluation or examination or test that actually doesn't modify the object we examine. So it keeps the object in the same state, which is advantageous in many perspectives, like you see for investigating the plane or gas pipes or anything. We cannot alter the structure because it would harm the structure and its functionality. NDT has a lot of synonyms. So sometimes you see NDI, non-destructive inspection, non-destructive evaluation, NDE, etc. And if you look in your field or in our fields, you hardly go to any branch without NDT or NDI, as you see further. So why do we need it? I already said it. We have a destructive test that gives us usually very exact information and very direct information of what we examine. But it damages material, like we see for the bending test, for instance. So we have certain limitations for further use of the thing we examine. And that's why people develop the NDT that give us certain freedom and also the speed of application. So we can measure in higher amounts much faster and we don't alter it. The problem is that we need to have a correlations usually with the data, with the material property or information we get, and then we need to interpret them through the correlation. So it's something like you would measure height of the building by measuring the shadow, let's say, as we see on the picture. So it's less And NDT, you may find it almost everywhere. There are a few examples here. When you meet them every day, you go to Sweet Machine, and when you put a coin inside, the machine has to investigate size, weight, shape, sometimes also metallurgic properties like electric conductivity, and so on. And if it passes the test, then you can buy your sweet little thing. Or metal detectors we use to investigate the electric cables in the walls, or finding some jewelry on the beach, detectors at the airports, and so on. All these things are actually non-destructive evaluations or techniques. So here is the situation with the plane or a gas pipe, and the division into the different synonyms we always use for NDT. Here is the example of comparison of direct destructive tests and, let's say, less direct NDT tests. So one test, the destruction, give us very direct property. We have a pure information, let's say, but we demolish, let's say, the project, the object. And using NDT, we get information that is not direct, but we need to find these strong correlations and interpretations of these correlations, like we see on the picture on the bottom, measuring the shadow by if we want to know the height of the building, for instance. So we need to know conditions also around. Here is the everyday example I just mentioned. So the sweet shop, I mean the machine shop, the detectors at the airport, or metal detectors for investigations of your terrains. And this is the slide we didn't touch yet. So we may see that our actually body also functions as an NDT. For example, when you use your hand and you put it above something hot, you don't have to touch it and you know that it's hot. So you get information. You can also get information about material kind or surface or size, shape by just touching without looking at it and without altering the properties of the object. Our smell is also very, let's say, that's the definition, maybe problematic, but let's call it still non-destructive. If we smell something, we know that it might be comfortable or uncomfortable compound around in the environment. Of course, the sense of hearing is very useful NDT technique or sense we have, because we can more orient in a space and of course within a time, so we can hear upcoming cars or somebody's calling us and etc. That NDT investigation that is done by our body. And of course, the most important is the sight. 90% of information we get is through the sight. So sight is our biggest source of information within a non-destructive way. So as you saw, NDT is always connected to transfer of information. And this transfer of information is done by the carrier. The carrier is a whole electromagnetic spectrum. So in our case, our body works in many spectra, visible, also slightly infrared. And of course, if you start investigating like a universe, you need to go to radio, gamma ray, and other spectra. So all these various ranges of spectra can help us adequately to the situation to get some information using NDT approach. But let's go more into the field of, let's say, experimental mechanics, where we deal, for example, with hygroexpansion of wood. And hygroexpansion, by definition, is actually strain. And strain is just a relative deformation. So we take the size of the object and then we measure the change of the size of the object. And the ratio between these two we call strain. And hygroexpansion is, by the definition, just a strain. So let's look at what possibilities we have to measure strain or hygroexpansion. The first categories we call extensometers. Those are these little machines that we usually clip on are specimen in the laboratory, for example, it's universal testing machine, and they clip from both sides, and then they actually move with the object that is being deformed or examined. They have very big limitations, and they are usually connected to this machine, so we cannot usually use them for Hygroexpansions, for instance. For that reason, we might use, for that purpose, we might use strain gauges, as you see on the pictures. There's a little electric or optical circuits that you actually glue on your object of study, and by altering the object, for example, by Hygroexpansion, you alter also the length of this circuit. And because they know the correlation between the change of the length and the displacement change, the size change, you can deduce also the strain. The problem of these strain gauges is that you need a lot of them usually, and in many directions to get information that is valid. Imagine you have a wood. The wood, there is a knot right in the middle. Where to put your gauges? Into the knot, above, or on the bottom, and so on. So to cover all the field, all the specimen, deformation or strain, you need a lot of them, a lot of gauges. So they are not that used in wood science for that reason. They are mostly for isotropic materials, polymers, metals, where it doesn't matter where you put them actually and how you orient them. Then you have a category we call interferometry techniques. You have many techniques there. It's tens of techniques that overlap actually. You have a holographic interferometry that is projecting some holographs on the specimen, and by the, let's say, subtraction of these two, you can deduce deformations. You have a speckle methods where you use laser and you create a random speckle pattern on that specimen, and by again some Fourier transformation analysis, you can get the data about deformation. Then we have a method called moire. You know, this effect on the comb, you see that you have two grids of different sizes, and when you start overlapping these two grids with different sizes, you have this special object or that appear, and we call them moire effect or moire objects. And from these objects, you can again deduce the deformation. Then there is a method that is very useful and is becoming very popular too. It's called chirography, that is connecting actually all these knowledge from the previous techniques together and providing more accuracy and maybe even more useful applications. So interferometry techniques are very important, but they have one big disadvantage. They're very sensitive for noise. For example, if you were measuring in a lab and next to your lab there is a tram line and the tram would go, you would probably see it on your measurement data. So they are very sensitive to the noise. And that's why people somehow started to think about the optical techniques, how to just get a deformation from the optical images. And among these, we have one big technique that is called digital image correlation, and also point laser triangulation that is now, let's say, marginalized because of the success of digital image correlation. So let's have a look at the digital image correlation in the perspective of time compared to the other techniques. For example, the DIC, the digital image correlation, you can see as a brown and red lines. So this is a number of articles that are utilizing these techniques in time. The brown is from Google Scholar, the red one is Web of Science. And the competitors of these techniques, you find on different lines that are keeping on the bottom. There is this gray line, SP, which is actually the chirography. It has just a very complicated name, but the common name is chirography. Then there is a blue line that is moire interferometry. And then you have it on again on two different sources, Web of Science and Google Scholar. So you see that these techniques actually were not used that much up to now compared to the DIC, and the success of these technique, DIC, is just because of ease of use and let's say functionality and applicability to any problem you want, including the Hygroexpansion. So if you were, for example, to measure it today, you start today and you don't know how, you probably would choose DIC today because it's easy to set, as you will see, easy to interpret the data, and very nice outputs can be presented too. So let's have a look. What is DIC? It's actually a method or technique that allows you to measure deformations. By deformations, we mean absolute and relative. Absolute is displacement, how the thing moves. The strain and curvature are already relative. They are first derivative and the second derivative of the move in a space. So they can both be evaluated, and of course, the more derivative you do in actually any application, not just with the image, the more noise you get. But that's the mathematics behind. The resolution, actually how sensitive the technique can be, is usually set about 0.02 pixels. And then it just depends on a scale you are doing it. If you are in a wood anatomy and you are measuring the hygroexpansion of the cell wall, your pixel might be, for example, few micrometers. So with this resolution, you get even into the, I don't know, hundreds of nanometers. So that's the sensitivity of a DIC. It doesn't depend on a size, it depends on a resolution of images, basically. And among these groups of DIC, we have three forms. The first one is two-dimensional DIC. As you see on the picture, we have an object and the camera that is actually imaging the area or the object. And this camera has to be placed perpendicularly to the object. So we are actually able to measure only flat areas because of the perspective that is actually changing the sizes of objects when you image it by one camera. But it can be very well used in microscopies, like electron microscopies, even AFM, etc. Usually we have one camera connected to the computer, then you have a good light source, and there is some kind of speckle pattern on the object. So that's a two-dimensional one. Very limited, but still very handy and useful, especially for the microscopies. The other form is a three-dimensional DIC, which is stereoscopical, and that allows you, it has a stereoscopical setup that allows you to measure deformation in 3D, but it's a deformation in, let's say, quasi 3D. Quasi is because you cannot get deformation inside and outside of the object. You can see how it moves towards and away from cameras, but you cannot see how the specimen, for example, shrinks or expands towards or outside the camera. So it's, let's say, quasi. So you have a displacement vector, the motion in 3D, but deformation just two-dimensional. You usually have two cameras, light source again, computer software, and because it's a stereoscopical, you need to also make a calibration because each camera has its own coordinate system, and this coordinate system has to be calibrated so they match together, and the point you are measuring with left camera is understood as a point you are measuring by the right camera. So this is the most common technique currently because it allows you to measure also not only flat but also curved. And again, if you think what happens to the object when you deform it and you measure it even though it's flat, you know there is a Poisson phenomenon. So anything that you deform expands, or anything you pull shrinks. And this Poisson effect is always present even for little deformations, and two-dimensional DIC cannot grasp it actually. So that's why this is the used the most. There is also a version of this 3DIC with a multi-camera option. So you don't have only two cameras, but you can put 5, I mean, you can put 4, 6, and more. And then you create the pairs, let's say couples of these cameras with the stereo matching. So then you can get actually information about the Hygroexpansion in all directions of the object, which might be, for example, handy or useful. So you just create the pairs and compute it as with the standard 3D DIC algorithm. And the most, let's say, sophisticated DIC system or form of the DIC is called digital volume correlation, DVC. And your image is not two-dimensional image from the camera anymore, but it's a three-dimensional image. And for a three-dimensional image, you need some kind of tomography. So either X-ray tomography or neutron tomography or magnetic resonance and so on. But once you get your object that is being deformed in a time, so you have a series of 3D images in a time, then you can use the DVC algorithm and calculate what is happening actually inside the object. That's the biggest advantage compared to the 3D DIC. Now you have information how the cells, for example, of wood deforms inside the specimen. So it's, of course, you are very limited with the space, and if you have to be inside the machine like an X-ray, and then you have to have also the testing apparatus there for your test. So that's quite limiting, but there are few examples already, and you will see one later on. Okay, so we now know what DIC is. Let's have a look how actually it started, what was on the path to get DIC. I cannot not mention Heinrich Lambert, physicist, mathematician, who actually defined the theory of perspective. That was 18th century. Of course, when you go to images and image correlation, you need to make and have image. So, you know, the first image was made by Louis Daguerre, Swiss scientist, again, physicist, and he created photography. At that time, it was not called photography, it was called daguerreotype, if I remember correctly. So that was the first images. In 19th century, we developed photogrammetry. And photogrammetry is a branch, actually, where DIC was used for the first time. So it was actually developed for the photogrammetry. So the actually observing the changes from aerial images. And this image correlation algorithm was prepared in 1961 by Gilbert Hobrow. He prepared the instrument actually to correlate these big images for a survey and reconnaissance to see what's happening with the ground conditions. Here we see actually his patent from 1960 for a first stereo image correlation machine. They were calling them stereo mats. So it was a huge machine. On the left, you see that there were two maps or two images put next to each other, two scanners, and they were trying to correlate the information between these two parts. So these huge machines were also here, I think, at the faculty, if I remember correctly, and you can still find them in the museum. Digital image came much later, so let's mention also this or acknowledge this. The first digital image was done actually for the purpose of transferring data about athletics or Olympics between Europe and the United States. It was in 1921. The first image was sent through the Bartlane cable that is laid or was laid on the bottom of the Atlantic Ocean. And that's how it looked like. So you see that it has maybe 8 grayscales. Of course, the computer development helped to get power to analyze the images. Then the chips was one of the biggest discovery of 20th century, either CCD chips or CMOS chips. We have them all in our cameras, in our telephones, and they were acknowledged also by the Nobel Committee in physics. They gave a Nobel Prize in 2009 for the principle of CCD chips, so for the getting information from the light and storing it as information. And so this was beginning, and now let's go to the first application of DIC in mechanics, actually. So what we actually wanted to use, because Hygroexpansion is strain and this is mechanics. So the Peters and Ranson in 1982 published the first paper, how they used DIC to analyze a loading or wave loading of some component. And Sutton, 83, actually was the first who developed a modern way algorithmically for the two-dimensional DIC. Sutton was one of the main author also on the software that created for the first. Okay, so let's have a look at these two basic forms of DIC, two-dimensional and three-dimensional, a bit more closely. Let's look at the assumptions we have to make when we use it. So two-dimensional DIC cannot examine out-of-plane deformation. So anything that goes away or coming towards camera cannot be understood. Why? Because imagine the situation that the object would go halfway towards the camera. Then by this algorithm, you would actually get 200% deformation. Your object would double, basically. And by the algorithm, it would be understood as a 200% deformation. So our assumption has to be following. We need to have a planar surface or flat surface, of course, because of the perspective. We need to have a surface that is parallel to the sensor. And then we need to keep the constant distance through the whole experiment, distance between the camera and the object. And this is actually very difficult to achieve because of the Poisson phenomenon, the expansion or reduction of size during the deformation. So that's the type two-dimensional thing. And let's have a look how it actually functions. So let's imagine that we have a point like this red cross, and this point has certain signature. Signatures means something unique. And now we have to track or search for this signature, how it's being transformed within a time. So that's called tracking. So we just need to search for this point in a time during the deformation process. And the signature is searched or tracked by so-called similarity function. And for the DIC, it's usually some kind of correlation. So we need to have this function to find the similarity between all the images within a time. But in the practical aspects, we cannot use just single point. It's not unique enough. Even though we have millions of colors, there is a chance, a big chance, that there will be some point with the same color. So the point is not unique enough. And that's why we need to use so-called subset, some kind of group of pixels that are neighboring our point. And by tracking this subset, these groups of group of pixels, we actually can achieve successful correlation, because it's hard to find if you have a randomized pattern made by some technique. It's hard to find the same pattern on big enough subset on the structure. So I mentioned that we need to have a stochastic or a random pattern on our structure we examine if we want to use DIC. So the conditions for our surface or pattern are following. It has to be high contrast, it has to be isotropic and non-repetitive. If you look at the first pattern on the left top, we have a high contrast, but we have a repetitive stripes, like a zebra stripes, and we have an anisotropic image, meaning that if you turn it for any angle you want, you will notice it. That's in image analysis called anisotropy. If you look at the bottom left, we get a high contrast. We got rid of repetitiveness, so it's, let's say, non-repetitive, but still it's anisotropic. On the right top, we have an isotropic image, which means that if you turn it, you hardly notice that something changed because it's randomized. It's non-repetitive, but it's a low contrast. So our ideal pattern looks like on the bottom right. That has these aspects we need to develop for our experiments if we want to use DIC analysis afterwards with these images. So that's how the images or the surfaces look like in a real. You can use classical sprays, black and white. So you first spray it white and then you just gently spray it with a black one. You see on the right side that there are some big speckles that actually are not correct, because again, imagine that you have this rectangular as a signature that will be correlated within a time. And if your subset, this rectangular, is small enough and it will fit inside this black stain or black speckle completely, then it might be difficult to track the position of this pixel that is surrounded by this subset. Very nice pattern for micro applications can be done by Xerox toner. It's very cancerogenic, but there are some ways how to do it. You open the old Xerox toner and put them into the box with your specimens, and then you just blow some kind of air, and then suddenly all this toner will start, the particles, the carbon will start flying around. Of course, you have to close the box. Then you let it go down. Once it touches the surface of your specimen, you can put it into the oven and bake it so it really adheres or touch and fix to the object, and then you can use it for your measurements. And this Xerox toner, these carbon particles are very small, so they are especially useful for micro applications. So anyway, you can imagine how to make such a pattern is actually available or doable. As I said, the DIC is very easy technique. You don't need much. You need just a camera and the software. And if you prepare the experiment with your pattern and you meet all these assumptions I told you, but you see they are not too harsh, then you can set up your experiments very well. Usually DIC algorithms functions with grayscale cameras. 256 grayscales is enough. You don't need more, so you don't need actually colorful cameras for this for successful correlation. Even 10-bit cameras are not used. It's too much data already with the grayscale or 8-bit images. The example is on the bottom. Imagine you have a camera with 1 million megapixel or 1 megapixel. So it's like 1000 by 1000. This is produced in a 8-bit, about 8 megabyte image. And now imagine that you make 10 images per second or 20 or 30. And your experiment is running for a few minutes. Then you see how much data you produce for just one single specimen. So that's why it's better to keep your acquisition times a bit lower, so you don't have millions or billions of images to process further. And 1 megapixel is really good enough still for most of experiments. Because of the sensitivity, I told you, this 0.02 pixels. Let's have an example how this correlation algorithm functions. Now we know that is actually tracking certain signature. So imagine that we have this object, this cross. So we see it as a black cross on the white background. The computer sees just the values of pixels. So let's put a 0 for black and 100 for the white. And now let's move the cross. up and right. So we see it optically, computers see just change of the structure of these numbers. And now the goal is to have a procedure how to calculate this change of the motion of the cross. So let's imagine we would take the subset that is 5 by 5, and we would calculate certain similarity function for all possible scenarios within this area. The possible scenarios are calculated through the correlation. This equation looks complicated, but it's very simple. Look at the right side. You have an image that is I with the X and Y that is in the middle of your subset, of your rectangle of this. That's this red mark. That's our I, X, Y. And plus E, which means to define our subset. So basically then you need to just take your image before motion minus image after the motion. So the motion is U and V. So that's the displacement vector. And this kind of sum, or subtraction is rooted and summed to get a result of correlation function. And the smaller number you get through this correlation function, the better similarity. So this function is called sum of the squared differences. Difference, you square it and you sum it. So it's pretty simple. If you look at our case, let's first calculate this function for the vector -2 and -2. So 2 pixels left and 2 pixels down. So we just take our values of pixels before and after. You can see this equation on the top right. So you see there is 100 minus -0 squared. So that's the actually position of left upper corner before. I'm not sure if you see my mouse, probably not. Minus top left corner after the motion. So there is a 0. And if you do it for all the pixels within this box, you get score 18. So this is our similarity for vector of motion -2, -2. So 18, we have 18. But let's calculate it for the vector 1 and 1. So 1 right and 1 top. If you calculate it, you get a perfect match. Our C function is 0. It cannot be smaller. The 0 is the perfect. So now we know that this point with all the signature around moved 1 and 1 as a vector of motion. So this is in principle what the DIC does all the time. It takes this box and then it goes pixel by pixel, unless you told him to skip few pixels to reduce the computation time. And it calculates this score. And if the computer finds the best score, it knows that your point with your signature moved somewhere there. The problem is that in reality, there is not such a simple situation. So our deformation is not pixel-wise, but it's also sub-pixel deformation. So you never get this similarity function like this SSD equals 0. It doesn't happen in reality. So sub-pixel motion has to be somehow handled. And the second thing, the shear deformation of the subset has to be handled. Shear deformation is seen here. So your rectangle before deformation we see on the left is actually not a rectangle anymore after deformation very often. So it's kind of skewed into this rhomboid shape, let's say. So the algorithm has to be robust enough to deal with shear deformation and sub-pixel motion. The sub-pixel motion is usually handled by optimization technique that transfer your raw data, those pixels, into the continuous function. So our discrete data from the image that we see on the top left are interpolated by using many different techniques, bilinear, bicubic, or bicubic spline. And this allows algorithm to actually handle the subpixel deformation, because suddenly from pixel to pixel, it's not just sharp step, but there is a function for the correlation. Okay, so that was the principle of 2D and also 3D, but let's talk about the 3D a bit. 3D is much more useful. That's how you always have it. You have a long bar with 2 cameras and some light in the front. This one is probably some kind of infrared light. Again, you can have if you have a camera that are infrared, you can measure in infrared spectrum, and the algorithm is the same. Then you see the images from the microscopes that allows you to evaluate little things like coins, etc. So it doesn't provide only the deformations, but also provide a topography of the object. 3D DIC basically works as our human sight. So we also have 2 eyes that allow us to grasp the 3D space. The same thing actually belongs here. If you have 2 cameras, you can get more plastic reality. Between the cameras, you actually obtain a 3D object. So the complication with the matching is this way. In 3D, you have basically two matchings or tracking, let's say. First one is stereo matching between left and right. So both cameras, both perspectives are met and they know about each other. And then you have this temporal matching. So these 2 sets of images have to be tracked, stereo matched within a deformation process. So it's it's more computational expensive than the 2-dimensional variant of DIC. I think I mentioned for this 2D, the problem is the perspective if you have a monocular system, but if you have a stereo system, you have to calibrate it. The calibration is done through the stereo triangulation. So it's very similar what people were using for centuries when they wanted to measure distances of objects from different angles. So basically it's one angle and another angle, and then by using a triangle trigonometry, you can deduce the shape and the distance of both cameras. The calibration makes you a common coordinate system that is very important for results, because these results are not then done in the perspective of either camera, but it's done on the base, on the common base, which is common coordinate system. If you make this calibration, you have to obtain 2 sets of parameters. One set is called extrinsic, and the other set of parameters is called intrinsic. So extrinsic is rigid motion, so how camera would move to another camera to get this perspective, and the second one are actually 2 perspectives projections on the objects. The calibration is usually done using a calibration grids or tables that are usually provided by the system you buy on the market, and you see they always have 3 points that are different, and then you have to make a set of images of these tables with the different angles, different distances, and the algorithm then searches for these 3 points and creates a lot of triangles that actually allows you to grasp the 3D object. Once you have a calibration and once you have actually motion calculated by DIC, you have to go to derive the secondary parameters, like the Hygroexpansion. I told you it's a strain. So the second step in DIC calculation is to obtain a strain. Strains are calculated very similarly as in a finite element method. So again, on this image of your object, they create artificial triangles, but now the triangles have a points where points mean vectors of motion. So it's a horizontal and vertical motion, and also the third axis motion. And by taking this into account, they know how this triangle actually changed its size. And then you calculate, let's say, general strain for the triangle. And then by using special filters, usually low pass filters, they smooth these triangles into the smooth contours that we can look afterwards. So for the smoothing, they use usually Gaussian or median filters. So you can see the principal filter on the bottom left. There is a set of parameters of the, let's say, R strain or Hygroexpansion, and median filter takes the subset again, makes the row of these things, and find the median of this subset. So it takes 4 and replaces number 10 as a 4. And that's how it smoothes the whole surface. So it looks like this then. On the left, you see the displacement. So this is the compression test of wood parallel to the fiber. So you see that there is already some angle visible where it will probably slide. It's still in elastic deformation, so you don't see deformation, but the software has sensitivity to see it much better. And then on the right side, you see the deformation that is called strain in a horizontal direction. So you see that strain is actually it's a derivative, so it looks a bit strange, but you have to take it as a field and analyze all the data you get usually for the sample to have a more representative. And that's the actually advantage when you compare it, for example, to strain gauges that you would glue on your sample. Here you have information at every point you are interested in. So we go to advantages to sum up the advantages of DIC. So I said it's a full field. Full field means that we have it on a whole specimen, non-contact. So basically it equals to hundreds of standard strain gauges. It captures local and global strains. We see it on the right picture. That is pulled by the tension. And now let's imagine these kind of deformations that is on the right, very right. We see that actually the sample deformed in a blue region, in a blue circle, but it didn't deform in the red one. So if you put your strain gauges into the red one to capture the strain, you would get 0 basically, because you would just hit the wrong place or position at the sample. The IC overcomes this issue, so you have the whole specimen that is measured. The IC also doesn't need many optical components like the other methods. You don't need any lasers, you don't need beam splitters, prisms, you don't need special tables for removing the vibrations and so on. So all these things are gone. The vibrations actually can be removed easily by rigid body motion removal from the image. Simple preparation of samples. I already showed you. You just need the way how to spray it, and you can work on many ranges or many scales. So you can actually calculate the motion of continents, which is also done. Applications also to earthquakes. How, for example, some kind of slopes slide after earthquake or anything, or you can work on electron images. So the range of scales is unlimited, let's say. You just need the image before and after some motion or deformation. There are many softwares you can use. The commercial ones are very sophisticated and very well done. And there are these 5 main ones. Correlated solutions are from the United States. Dantec and GOM, I think, are German. LaVision is French. And Excite is actually here from Brno, Czech. And then on the side, you also have a free open source codes that you can use. For example, I recommend them to use for educational purposes, especially the system called Moire Opticist 2 and 3D. We always have some educational activities, and so students can download it and work with the systems at home and give you just the outputs. So they don't have to come here for these correlated solutions we, for example, have, or Excite that we have licenses. Also, MATLAB has a DIC toolbox, but then again, you need a MATLAB for it. And applications of DIC in wood science, there are many. As you saw, the advantage is that wood science needs something that is so complex and sophisticated to grasp the variability and heterogeneity of the material. So any standard material testing, tangent compression bending, shrinkage and swelling, creep, crack propagation, delaminations, Poisson ratios, even vibrations are being done by DIC. Connections, and of course also the verification of our finite element models. Let's have a look how DIC, for example, look like in history. So this is the image from a publication of Zinc et al. From 1995. So the post-processing of the data didn't exist. They had just the contours with the values, but that was 95, and they still made very good measurements and very helpful findings. So this is a wood, I think, in compression. If you look a bit further, we go to Choi 1996, who used DIC to evaluate actually the fracture. So he wanted to see also the crack, which can be seen on the bottom right image. You see that there is this open area that is actually the crack inside the material. And now I will show you how it looks today when we analyzed crack in the, so here you see a beam that was loaded in a 3-point bending test, and the crack initiated very close to these green points. And all the modern system allow you to work with the points, with the lines, so you can really retrieve deformation with the time at certain points, as you see on the part B at the picture. So now you have very nice data for the presentation and also helpful for abstraction of the problem. Going back to history and also Hygroexpansion, this is the example from Murata and Masuda, 2001, who analyzed actually wood cell sorption and swelling due to sorption in coniferous species using confocal laser microscopy. So they basically photographed late wood and early wood cell walls before and after, and created these graphs of the swelling at a certain point in a, let's say, radial system. This is example how it can be applied for wood plastic composites. You really easily can identify the places of deformation composites. So you see it's not just one place, but it's a gradual deformation at many places due to the probably wood particles. Wood particles were also analyzed here. That's a very good example. It's particles in a polymer matrix. So working on the micro level, and then you can make a cut using some line and make a profile of the deformations at your, let's say, area of interest. Here is example from Serbia, from Professor Nestorovic, who are analyzing furniture using DIC. And here we see a very nice work from Sweden, from Forsberg et al. 2010, who actually made this DVC, this digital volume correlation. So here on the left, we see the specimen in a 3-point bending test. It had few millimeters only, and it was inside the X-ray tomography. So then they made a series of 3D images within a time, And as you see on the right bottom, they were able to calculate deformation also inside the wood. So they could see where actually the crack started, if there was a crack, I don't remember, inside the body. So that's very, very useful for pure wood science. Here are examples what we did with Lech Mushinsky. And I have it here only to see the complementarity of finite element simulation results that you see on the right side and the DIC outputs on the left side. So if you synchronize the system also the contour-wise, then you can have very good match also optically, not just in terms of the absolute values, of course. Here with ArcoX, we also use the DIC for tree mechanics. So this is how we measure in terrain. You see that we put a pattern on a tree and we don't need black and white because tree is already, let's say, dark enough. So we just spray random white dots, even of this size, but the size of the dots actually corresponds to our distance we chose for our measurements. So you see the strong lights down below the cameras, then you have a computer, a lot of cables, etc. And then you are able to get deformation of whole trees. This is from different measurement, but the same principle. So you see on the left, the horizontal deformation of the tree we made by pulling. On the bottom, you see the markers that was done for the different analysis, but again, using DIC. So you don't have to have just a pattern of sprayed, but you can also use just the points. And again, you can use the DIC. And then you see our, let's say, stages of bending, our cycles, how we loaded it. Okay, and here we go to our conclusions. In my opinion, DIC is irreplaceable in any mechanics, especially with science, because of the materials. We have a lot of done, 2 decades of using of it. It actually became a standard. It's nothing new or super new anymore. It's become a standard. We can say that it's really easy to set it up. Just don't be afraid, just take a camera, meet the conditions I told you, and start acquiring and then download some software and try to play with it. It's a great source of verification of our simulations. That's why we use it here very often. And we have to notice that 3D system is much more convenient than 2D because of the advantages of out-of-plane motion that is captured. Disadvantage is that you get too much data. It might be helpful for the future when you have a really time to play with the data, but it requires a lot of storages, a lot of thinking what to do with data before. So a lot of thinking is there too. And DIC is really now NDT core technique. There's you saw it in the graph in the very beginning. It became super poppy. There is a boom of DIC like techniques. Here are the used resources where you find more. And hereby, I will like to thank you for your attention. And if you have any questions, let me know.
Hello everyone, my name is Richard Slavik and let me introduce dynamic vapor sorption. What a sorption is? Sorption is physical and chemical process which describes attaching one substances to the another. It could be divided to the absorption, physisorption, and chemisorption. What the surface is or why the solid-gas interactions are important. It could be described by this simple model with a small cube with 1 meter edge and a small cube with 1 micrometer edge. You can see that the area of this cube is in similar ratio, and it's easy to calculate that it's 6 meter or 6 micrometer. But if we consider the bigger cube, which consists of the smaller cube, the area of surfaces of these cubes are much huge higher, and it's 6 terameters square. So, and this is how the surfaces on the porous materials are working. Sorption. Sorption could be divided to two basic process, and this is absorption and adsorption. Absorption describes the bulk absorption and absorption to the lattice structure, and absorption are describing the hemisorption and physisorption. It's divided based on the strength of the interaction. Hemisorption takes a large interaction potential, and mainly it's restricted to the single layer of the molecules on the surface, whilst physisorption is fundamental interaction forces are van der Waals forces, and these interactions are very big. On the pictures, you can see this interaction energy from the planar surface. On the both pictures in the z-axis, you can see the distance from the surface and how the energy potential or interactional energy are changing from the distance, with the distance from the surface. First theory which can help us describe the surface of the materials was done by Irving Langmuir, which is also known as like Langmuir theory. And this absorption model works on a theory that surface have some sides which are occupied and unoccupied, and the ratio between occupied sides and the total sides of the surface is proportional to the partial pressure of the ambient. And based on these statistical theories, could be derived a formula for calculation surface of the material based of known diameter of the molecules and so on. But real materials not work so easy, like these simplified theories from the history, and the surface are more curved, and it's not straight or planar like we expected, and it's bring further problems which could be done by next theories. First of all, we can consider that we consider three basic kinds of pores: macropores, mesopores, and micropores, which are divided to these categories based on the diameter of the pore. The macropores energy profile, potential energy, seems like energy profile of planar surfaces, but if you look on the right side, the micropores profiles are affected by each other side of the pores. So these mesopores and micropores pores are working a little bit different, like the classical micropores, which was introduced before. So from these theories was 6 groups of sorption isotherms derived, and you can see more information about it in specialized literature, for example, like here is mentioned. Back to the more sophisticated models. One sophisticated model was done by Brunner Emmett Teller, which is known like BET theory, which helps us calculate surface area of the porous materials, which takes multi-layer absorption on its surfaces. And from the point of introduction to the theory, it was maybe everything what we need, but now we can a little bit look about application of sorption in our technical purposes. First of all, or the most important, is try to use characteristic of the materials from pore structure and pore size distribution point of view. We try to measure surface area of the materials and also surface energy of these materials. We are measuring sorption and desorption isotherms and investigating hysteresis of the materials, as well like surface interaction with moisture or hot vapor or solvents vapors. We also need sometimes testing stability of the materials, especially in pharmaceutical and food industry, and or investigating the phase change of the materials affected by moisture. Analysis of pore materials could be done by various methods. Maybe the best known methods or well-known methods are mercury intrusion porosimetry and gas absorption. These two methods are very common for material characterization. Each device covers a little bit different scale of pores. Gas absorption takes mesopores and micropores mainly, and mercury porosimetry covers macropores. The dynamic vapor sorption could cover this micro and mesopores area and a little bit part of macropores also. The sorption and technical aspects like building physics and the material engineering many times use classical sorption methods, which are normally standardized by technical standards, European and international technical standards. And for these purposes, we are using the climatic chambers or desiccators with salt solution. We have tables, chemistry tables, which are describing salt solution and the partial pressure above the salt solution in closed jars. It's the classical methods, or we can use the climatic chamber with the digital managing environment inside the chambers also. And the samples are stored in these conditions, and in time they reach the equilibrium, which is set or planned. But these classical methods have many disadvantages, and you can see it's something like you can see on this picture. It recommends washing the cat. Yeah, it's first of all, this sorption is a very slow processes, and if we are using the huge sample, because of laboratory mass need some amount of sample. These samples are have significant dimensions, and also the diffusion and further things are taken into account, and the absorption takes a long time. Next thing is these processes are very sensitive to the temperature and the ambient pressure, and you can see it on the right side. If we have the desiccator with the samples which reach equilibrium, and we open these desiccators, the equilibrium is over, and molecules try to evaporate and go away immediately. So these processes can significantly influence results of the sorption. Yeah, it's something like washing a cat, because cat go away from the wash basin, immediately remove water to the environment. These disadvantages we try to remove by using of dynamic vapor sorption, which principle you can see on these pictures. The first advantage of this method is continuously measurement of the mass of the samples. These measurements, it's with precise temperature and pressure control, and we can also change in time environment of this experiment, which is very useful, and we can take next advanced methods for measurement or investigation of properties. The samples are smaller, which gives us faster results, more accurate and more precise, with higher repeatability and so on. Two basic types of dynamic vapor sorption are on the picture. On the left side, you can see classical hang-down wire device. On the right side, you can see carousel dynamic vapor sorption device. The hanging wire devices are more accurate because of more sensitive balance, and also the risk of contamination of samples are not present here. But carousel device is faster because it's testing more materials in one testing run. So it's more powerful if the samples are many kinds of samples, but on this hanging wire DVS are slower in this case, but more precise. We have this kind of hanging wire DVS systems in Josef Resel Research Center in Utechov, and this DVS has two pens. One is sample pen on the left side. Next is reference pan on the right side, because the molecules go to the sample and reference pen also. So this sorption on the hanging wire and pans are subtracted from the results. So the results are more accurate, like with DVS with one hanging wire. And also we have two inputs of gas reservoirs, and we are able to do sorption of water vapor. And on the second reservoir, we can have organic solvents, and we can do sorption one on the second reservoir, or do something like co-sorption, both reservoirs together. And we are mixing ratio of this dry gas and gas flowing through the reservoir, and mixing some specific ratio of partial pressure inside, which is measured by ultrasonic sensor or probe for relative humidity. Samples are measuring with microbalance in time, so we have signal of partial pressure and signal of changing of mass in time. What are the benefits of the DVS systems? First of all, the results are more faster because we have smaller samples and we have continuous measurements. This kind of measurements are more accurate, and the results have higher repeatability and reproducibility. We can also use organic solvents, and we can use also co-absorption. And the DVS system have precise temperature regulation, so we can run these experiments in a huge range of temperature also. DVS with changing partial pressure in time with steps or ramp could be used for some advanced kind of measurements, and also it's offer visual inspection of samples during the experiments by camera or microscopic camera, which is present in the DVS system also. We can measure sorption and desorption isotherms on this kind of analysis. We can measure cycles of this sorption and desorption and investigate the hysteresis behavior of the materials. We can also do surface analysis, focus to the surface energy and surface area, as well as we can measure heat absorption, use diffusion analysis. We can investigate amorphous content of the samples. We can do permeability test, phase transition, visual analysis of samples during the sorption, and also DVS allows use Raman or ER sensors and measure these samples during the sorption process. Sorption and desorption analysis looks like on the right pictures. You can prepare some specific profile with partial pressure and time. Steps of the partial pressure could be run by specific time or until you reach some specific equilibrium, which could be determined by derivation of mass in the time. And from these measurements, you can obtain this signal, which is mass and partial pressure or target partial pressure, which should be in the test chamber. from the sample. On the picture, you can see response of brick material from aerated concrete to the relative humidity or partial pressure in the experimental chamber, and few cycles desorption and sorption. From this kind of measurements, we can get this kind of sorption and desorption isotherms, which we are using for modeling heat and moisture transport in building components. As you can see on the picture, in pharmaceutical and food industry, it's very important hysteresis investigation of desorption and sorption cycles. From application note of producers, you can see a few pictures which are investigating materials from this point of view. Further analysis allows to identify surface energy or equilibrium spreading pressure, which is net change in surface energy due to absorption of vapor on the surface, as well as we can, on some theory, can measure surface area based on BET theory. Like you can see on the picture. The main advantages of the DVS system is that we can do this test, BET, in room temperature, because the normal devices which are using gas absorption are using temperature which is very, very low, and some kind of materials are not usable for this kind of measurement since its nature. So further parameter which could be measured is heat absorption, when we can do these measurements in DVS, as well as diffusion analysis. These diffusion analysis could be obtained from dynamic response of the material when the sample is put to the experimental chamber on the abdominal layer, and we are changing ambient pressure, and we are measuring the mass response in the time, and from this response we are able get a diffusion coefficient of the materials, as well as we can do permeability analysis, which is based on steady state, and for these purposes we are using small diffusion paint cell, which takes a small test specimen, small slice of specimen, which is placed between two O-rings. This cell is closed with some desiccator or salt solution in this chamber, and this chamber is put on the hug-down wire. And in the time, we can change the relative humidity of pressure in the chamber, and from this we can get not only constant diffusion parameters of the materials, but also we can also get the dependency of the diffusion parameters dependent on the relative humidity of partial pressure in the chamber, or the difference between pressure in the chamber and in the diffusion paint cell. So next area which the DVS could be used is amorphous content, and we can investigate the glass transition point and recrystallization phase. You can see some pictures from application data from the producers, where based on the experiment with changing relative humidity, we can measure these points, as well as we can use the camera and capturing these pictures from the states of materials in the DVS system also. So, thank you very much for your attention. This was from my side everything that I would like to say about DVS and the brief introduction to DVS system. If you have any further question, please feel free contact me on my email. Thank you very much.
So I will present you some information about this special technique that we have at the Thünen Institute in Hamburg. So the cellular UV spectroscopy is based on the electromagnetic spectrum, especially in the range of the UV light. So here you see the range between 200 and 400 nanometers, and our device is able to go up to 700 nanometers. So we also reach the visible light. And the principle based on this technique is the transmission and interaction of the UV light with the sample according to the Lambert-Beer law. We heard already something about John Heinrich Lambert in the DIC presentation of Václav. So here we got the combination of Lambert and Beer. And it says that we got A as the absorbance UV light that comes from the cell wall due to the absorbance of lignin. Then we have the extinction coefficient and the volume connection, as well as the thickness of the absorbing layer. So when we transfer this principle to the wood cell walls and the wood especially, we talk about the intensity that is measured by passing through the embedding medium through the cell lumen. So it's called I0, and the energy that is passing the cell wall layers. And we got this equation, the basic equation from the Lambert law, and we got this information about the absorbance A, and it's derived from the logarithmic value of the emerging intensity from the lumen divided by the emerging intensity of the cell wall. These are the physical backgrounds. And now we have the sample preparation. You already saw some nice pictures by in Anna's presentation. Here we have the sample size. It's about 1 millimeter to 1 millimeter in the cross section, and then about 5 millimeter length. And here we have a picture of the vacuum embedding in the epoxy resin according to Spur. So it's a very mild embedding system. You can use this one, or you use capsules. And then you have to use an ultramicrotome to prepare the semi-thin sections of about 1 micrometer thickness. Afterwards, the sections were mounted on quartz slides, and the result looks like this. This is an overview picture, and we stain it. So we get a nice overview of the cells we want to look at, and then we put it into the device. So this is the universal microscope spectrometer. It looks like a microscope, and you get the UV light that transmits through the sample. This device is able to scan areas, and here we have constant wavelengths, and these it depends on what you want to look at. If you have a softwood or hardwood, you use the maximum of absorbance for lignin. In softwood, it's about 280 nanometers, and in hardwood, it's 278. This device is able to have a very high geometrical resolution, about 0.25 micrometer to 0.25. And the photometric resolution is about that we detect 4,096 grayscale levels. And these grayscales were converted into 14 basic colors. It's seen on the right side. So 14 colors. So we get really nice pictures in that can be depicted as 2-dimensional or 3-dimensional image profiles. And these were also statistically evaluated in a semi-quantitative lignin distribution. So with this device and this equipment, we are able to visualize the lignin distribution in the wood tissue. And we are also able to show the lignin concentration. Another tool is the point measurement. So we can just look at individual cell wall layers. Here we use varying wavelengths in the range between 250 and 420 nanometers for the cell walls. And when we want to look at extractors or other things within the parenchyma cells, for example, then we choose a little bit higher wavelengths up to 600 nanometers to get all this information in the wood. Here you see the spot size. So yeah, we're able to analyze even just the middle lamella or the cell wall corners represented by the red dots, the stew layer, or even the deposits in the cell lumens. With this equipment, we have the possibility to analyze the spectral behavior of different cell wall layers and the deposits. So the application possibilities, I will present you three different projects where we use this technique. You have already seen the project of Anna, where we want to look at the tannin distribution in the impregnated wood. The first thing I got in touch with this method was in my diploma thesis. I had the chance to look at waterlogged wood after 100 years. It comes from the Panama Canal. And there was, during this construction from the canal, a very large area has been flooded, I think so. And it's a very big, large area, and they didn't cut all the trees. So the trees are still fixed in the ground, and yeah, so they are still there, and now they can be harvested, and there are a huge amount of different tropical species as Masaranduba, Kumaru, and Andiroba. Andiroba is comparable to mahogany, so it's a very valuable wood. And here we got the question, are there any detectable changes in the topochemistry of the wood cell walls? And yeah, we prepared the samples and we had a look at the ground tissues, the fibers. And this is the result we get from the UMSP. On the left side, you see the two-dimensional picture, and the bigger one is the three-dimensional. And here you see the concentrations of the lignin. We have a highest concentration in the cell wall corners, and it decreases to the cell wall lumen. So that looks pretty fine. And after 100 years in the water, nothing happens to the cell wall structure. So we have very nice wood that can be used. Yeah, that can be used for indoor applications. What else do we want to know? What about the point measurements of this individual cell wall layers? Here we got, oh, I'm sorry, it's in German. Here we see on the x-axis the wavelengths, and on the left side, on the wire layer, the extinction. And the maximum absorbance occurs around 278 because we have a soft hardwood species, and that occurs in this region. And we see the highest absorbance intensities are measured at the cell wall corners, followed by the S2 layer of a vessel. And here's the highest absorbance for the combined middle lamella. What else we want to do to look at? These are the deposits in the parenchymal layers. So we wanted to know if anything changed here in the composition. So the parenchyma is depicted in the red line, and these are located in the lumen of the cells. So they are not impregnated. We have them just in the lumen of the cells, especially in the parenchyma cells. These are aromatic compounds, and what we detect are the chromophoric groups. And these compounds are responsible for the nice color of this tropical wood species. The next one is, for example, the fungal degraded wood tissue. Here we are looking for initial decay pattern. and what happens to the lignin. Rehbein and Koch investigated Pinus sylvestris, and it's degraded by brownwood fungus and Rhodia violante. And the two-dimensional picture shows you with the arrows several areas with lower intensities, so the brownish one, and some areas with higher absorbance intensities. And it also can be depicted as a three-dimensional graph. And you also see the histogram that gives you the statistical evaluation. That means during the wood decay by brownwood, the lignin is modified, and that's why it changes its absorbance intensities. And this is very nicely shown with this technique. And the last example I would like to show you is the furfural alcohol modified wood. So it's my topic of my PhD thesis that I finished now. So we want to know, is it possible to use this UMSP technique to investigate this furfurated wood from the infrared results? We know that it has a very high fluorescence properties. So we had to adapt the technique and change the thresholds, and afterwards we get really nice pictures. This is the untreated radiata pine, and this one is the treated one. So when we compare both pictures, you see a clear difference from the pink reddish pixels to the green ones. So we have an intensive modification of the whole cell wall layer shown by these high absorbance values. So this technique is absolutely great for investigate this impregnation and how good the cell walls are impregnated. So I just put everything together for a quick overview about the cellular UV spectroscopy method. We have a topochemical, we are able to characterize the cellular level of specimen. It's a highly sensitive method with a high spatial resolution. And the very special thing is that we have an in situ characterization. So you have the wood tissue exactly at that point where you want to look at. So you don't destroy everything and just look at single components. You have just the wood tissue as it is, or as it was in the board or in the larger sample, and you can look just at this point. So you are able to analyze fungal degradation pattern. You can analyze lignification, deleafnification, or lignin modification. So it's also very valuable for investigation of the wood formation. There you can follow the lignification of the cell walls. And as we saw for the furfural alcohol, as well as for the tannin, we still have to evaluate this. It's possible to analyze modified wood. The disadvantages are the elaborate sample preparation. So it's very takes some time to prepare the samples, and you just have a small window you open and look at a very special size of your specimen. So it depends on the research question if this method is useful for your analysis. This was a short overview of the UMSP technique, and you're welcome to ask any questions now or via email. Thank you.